This is our presentation on the dynamic control of an Apache's 30mm gun turret. This is the Northrop Grumman AH-64 attack helicopter. It utilizes the M230 chain gun turret, which is about 1.2 meters long with a field of view of 220 degrees in the azimuthal plane and an elevation range of 71 degrees. It holds 1,200 30mm high explosive dual purpose rounds. Each round imparts 189 Newton-second impulse. The aiming method uses the orientation of the pilot's helmet to aim the turret. This attack helicopter is designed for precision during hover and maneuvering. Unfortunately, most of the specifications are classified.
The equation and motion describe how the turret rotates in yaw and pitch when its torque is applied. Each equation has inertial, dampening, and stiffness terms, just like a second-order system from homework 7. A turret angle's velocity and acceleration all work together to define its motion, so it behaves exactly like a classic second-order rotational system. And because the turret angles change smoothly over time, its motion is fundamentally continuous. So in our analysis, we treat the turret as a continuous time dynamic system.
The system takes three inputs: the pilot's desired line of sight, the fire trigger command, and helicopter motion disturbances to be filtered out. It outputs the turret's position and angular rate, the actual targeted line of sight, and the firing outcome. We measure turret position and motion with encoders and gyros and line of sight using onboard sensors and helmet orientation. This system uses a continuous feedback loop. The controller compares the pilot's desired line of sight with the turret's measured angle, and any difference becomes an error signal. That error drives a commanded torque to the actuators, keeping the turret aligned with the intended direction.
We describe the turret motion using a few coordinate frames. First is the helicopter body frame, fixed to the airframe. The turret azimuth frame rotates left and right about a vertical axis relative to the body, described by the azimuth angle. On top of that is the elevation or gun frame, which rotates up and down about a horizontal axis relative to the azimuth frame. Together, azimuth and elevation define the line of sight frame, which is the actual pointing direction of the gun. For each turret axis, we assume a PID control law. The command angle is compared to the measured angle to form an error, and the PID controller uses that error, its integral, and its rate of change to compute the motor torque. The torque is then applied to the turret dynamics, driving the azimuth and elevation gains to track their commanded values as closely as possible.
Show a closed-loop control system for an Apache turret. The command angle, as shown by R as a function of S, enters the summoning junction where it's compared to the measured angle coming from the feedback path. This difference forms the error signal, which is fed to the PID controller, which generates the actuator torque command and drives the turret. The GFS block describes how the turret physically responds and rotates based on its inertia and dampening. The output angle, Y as a function of S, is then measured and fed back to continuously correct the motion. In conclusion, the project showed that the Apache turret operates as a fully controlled dynamic system. By modeling its yaw and pitch axes with the standard equations of motion, we demonstrated how the turret responds to the actuator torque and external disturbances. Using a PID controller with continuous feedback, the system can correct any errors to stabilize the turret and accurately follow the command angle.